We now know that if we have a transmission line with characteristic impedance Z0 and a voltage wave travels from some source along the transmission line to a load, we're going to get some reflection coefficient, or we're going to get some reflected voltage wave, and the amplitude of that voltage wave is determined by the reflection coefficient at the load, which is just equal to ZL minus Z0 over ZL plus Z0. And what happens then is that the voltage along any point along this transmission line is the sum of this incident wave and this reflected wave. That leads us to another type of impedance that we can define for the transmission line, which is called the input impedance. And the definition of the input impedance is the total voltage along a transmission line as a function of distance to the total current along the transmission line as a function of distance. I equal V over V of Z equals I. Zn is equal to V of Z divided by I of Z. And this is for specific Z, right? Z equals some distance along the transmission line. So I want you to notice two things about this equation. First is that input impedance is total voltage divided by total current. So it's different than the characteristic impedance Z0, which was either forward voltage and forward current or reflected voltage and reflected current. So they're not the same thing. The other thing I want you to notice is that input impedance is a function of distance along the transmission line D. Therefore, unlike characteristic impedance, which is constant for a transmission line, input impedance will change depending on how long the transmission line is, depending on the length of the transmission line. The math for calculating the formulas for input impedance is pretty long and pretty tedious, even for me. And as you've seen from these videos, I tend to like tedious math. But in this case, I'm just going to break my rule, and I'm going to just go ahead and give you the formulas for input impedance and not even worry about any of the derivations. So the first is for the lossy case. So the general formula for input impedance along a transmission line is going to be Zn of D is equal to the characteristic impedance times this big quantity that is load impedance plus characteristic impedance times the hyperbolic tangent of the complex reflection coefficient times L divided by the characteristic impedance of the T line plus the load impedance times the hyperbolic tangent of the complex propagation constant times the length. Gamma is the complex propagation constant. I think I called it something else just a second ago. Complex propagation constant. This equation can be simplified for the lossless T-line case. Zn as a function of D is still equal to the characteristic impedance of the T-line times this big messy quantity, but we can reduce this quantity a little bit, and it's ZL plus J times Z0. Now we just have the tangent, and the argument of the tangent, instead of being the complex propagation constant, is now just the wave number. And in the denominator, it looks pretty similar. Z0 plus JZL tan of beta L. So those are the two formulae. Not all calculators can perform these hyperbolic trig functions. So if you've got one of those tiny little handhelds, you're kind of going to struggle with that. But the TI-89 can. So for your coursework, if you don't possess a calculator capable of hyperbolic trigonometry for the homework, you can use some sort of online calculator like Wolfram Alpha or something like that to calculate these hyperbolic functions. And I won't give a calculation of input impedance for a lossy T-line on a test where you would need to have a TI-89. So you'll never have to do that on a test. I'll give it to you in the homework. You can use online tools, but I won't give it to you on a test since you might not have a calculator that can do that. So what's the utility of calculating the input impedance? Well, really the big advantage is that I can take this entire circuit, transmission line, of a fixed length and a load, and I can replace it with a circuit model that is just Zn. And that's really the big utility, is that we can replace a T-line and the load with a circuit with an equivalent input impedance. It's a really nice technique to use.